Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review of concepts from your trigonometry class. As such, I do not delve into the proofs of theorems, nor do I go into excruciating detail with examples. If you've never had a full course in trigonometry and you're currently enrolled in a pre-calculus course, I highly recommend watching my trigonometry playlist on YouTube as it goes into greater detail with all the trig. Again, trig is so important for calculus that having a shaky background in the subject will lead to abysmal results in calculus. That being said, let's go into a review of the law of sines. Now, the law of sines is the first part of trigonometry where you start dealing with non-right triangles. So this theorem applies to any triangle, not just right triangles. It could be obtuse triangles, it could be acute triangles. So you could have a triangle that looks like this, or you could, which usually even my intended non-right triangles end up looking right, but that's supposedly not. And something like this. There we go. Okay. So the law of sines can apply to either of those triangles. And what it basically allows us to do is it allows us to create a ratio between the sines of those angles listed there. In fact, I'll just write it on both. That's angle A, angle B, and angle C, and their corresponding sides. So side A, side B, and side little c. You know what? I'm going to make capital C's look actually capital here. I use a bracket here for capital C's so that it's a little more obvious. I'm going to do the same thing down here. That way there's no question on which C I'm talking about when I'm handwriting here. Anyhow, so this is an incredibly powerful theorem, and we are going to go ahead and showcase or recall how we use this. And I should mention that you should have actually already seen the proof in your trigonometry course. If you're interested in the proof, I have it in my trigonometry series on YouTube, and I highly recommend watching it, especially if you've never had a trig course, like I said earlier. So how do you use the law of sines? Well, in a general, very easy case, you're just given the triangle ABC and you're asked to solve. You're given parts of that, maybe a side, an angle, maybe a couple angles and a side, or maybe a couple sides and an angle, that type of thing. But you haven't been given the whole triangle, all the information. So the best way to tackle it is to make a table of values with one column representing the angle. So I'll show you what I mean. So let's suppose that you're given a triangle, and again, that's supposed to be a non-right triangle. It could be a right triangle, by the way, but all my triangles end up looking like right triangles. Almost all of them do. And let's suppose that this is angle A, this is angle B, this is angle capital C, this is side little a, side little b, side little c. And let's suppose that somebody, say angles here and sides. I normally don't label the columns, but let's just pretend. Okay, so angle A, angle B, angle C, side little a, side little b, side little c. And I'll write in blue, or maybe green. I'll write in green what we have been given. So let's suppose that somebody tells us, oh, by the way, angle A is 37 degrees and side C is 12. And let's also pretend that side A is, I don't care, 18. So we filled in what they've given us, right? And so now if I go back here to the how-to, which I would never do if I was teaching this topic, but instead I'm just reviewing it, and so I assume you've seen it. I make that table, I fill it in with the given information. There we go. Now, ignore the rest of this sentence or this step right here, because that will become important in a moment when I change the situation. But for right now, if a row of this table is filled with known values, then we can use the law of sines. So if I look at this row, or if I look at this table and there's a row that's filled, which there is, then I can totally use the law of sines here. In fact, let me change this, because now that I think about it, I'm giving you the ambiguous case and I don't want to do that here. So let's pretend that angle A is 37 degrees and angle C is 32 degrees. That's actually probably better. Okay, so in this case, still, I have a known row, and I can therefore use the law of sines. The law of sines basically says I can make ratios to find the unknowns. Well, the first thing I can actually do is, if I know what angle A and angle C are, I can add those up. That'd be what, 69 degrees? And I can subtract that from 180, because you only have 180 degrees in an entire triangle. And the remaining angle is actually what B is, right? So let's see, 111 plus 69 is 179, plus 1 is 180 degrees. There we go. So this is, that fills out the triangle as far as the angles go. So that was pretty easy. That was arithmetic. But now we're going to use the law of sines. And the law of sines just says that side C is to the sine of angle C, as side A is to the sine of angle A. And you can see that there's only one unknown there. Okay, so that's how you would go about it. I'm not going to solve this out, but that's how you would go about that. We'll do an example solving things out in a bit. All right, now, and that's all you really need to do. However, let's see, I'm sorry, fill in, that highlighted piece was important. I actually just did it. Let's see, fill in the given, if a row is, then, okay. Use the ratios of law of sines theorem to solve. However, if an angle is unknown, you must check for the ambiguous case. This is the part I meant to highlight. So let's suppose I change this slightly here and go back to what I originally wrote down. And let's suppose that I say that this side length, again, is something like a 16, or I think I had it as a 12 before. That doesn't really matter to me, but okay. I could still use the law of sines because I have a full row. So I could use the law of sines to find out that angle. Unfortunately, this opens up the possibility for ambiguity. And so when we go to solve this triangle using the law of sines, you would say, okay, well, the unknown here is this angle C. So I'll say the sine of angle C is to its side, 12, which is C, as the sine of angle A, which is 37 degrees, is to its side A, 18. And then you would multiply both sides by 12. In this one, I'm actually showing the steps because there's something important that needs to be said here. And let me just finish this out, 37 degrees. And then you would find out what C is using the inverse sign. So this would imply that it's not actually C, but C hat is equal to the inverse sign of that 12/18. Notice I don't bother reducing that because I know I'm grabbing a calculator. So I just leave it as it is. So I know that the reference angle for C is that sine inverse. Now let me just step back a little bit here, because I have actually within this one kind of motivational topic done a few things that might throw people off. One thing is that when I wrote down the initial ratio in the first kind of quick example, I wrote down the ratio as A over sine of A is equal to C over sine of C. You should know that if two fractions are equal to each other, their reciprocals are equal. So this theorem can be used as written, or you could take the reciprocals of everything and they would still be equal. So that's one thing I just wanted to mention there. All right, that being said, let's go ahead and hop back. And let's talk about this reference angle. Why is it a reference angle? Well, it's sine inverse returns, all inverse functions return angles only, right? So the sine inverse is just going to return some angle that I'm saying is a reference angle. And technically speaking, it will only return angles between negative pi over, well, we're in degrees, so negative 90 degrees to positive 90 degrees. This is an issue. Not the negative part, honestly. When you're working with triangles, it will never, your reference angle will actually never return a negative number. So let me go ahead and just say, but in reality, what we're going to get here is C hat, the angle, is actually just between 0 and 90 degrees because we're working within a triangle, so our ratios are always positive. Every number we're dealing with is a positive number, so you don't have to actually worry about that. But the main thing I want to drive home here is that the reference, what a sine inverse is going to return in this situation, is always an angle between 0 and 90 degrees. Now, I hope you can understand, if you take a look at our triangle, there is a possibility for an angle here being greater than 90 degrees. Now, I know the way I've drawn it, it's not the case. But what if, just what if, the triangle actually looked like, that's not how I want it to look like. What if the triangle actually looked like this, where this was angle C, this is angle A, and this is angle B, this is side C? What if that was the case? Well, the inverse sine would never return this angle because that angle's greater than 90 degrees. And so that is a major, major issue. So the law of sines has what's called the ambiguous case, which is when we run into that situation where C, the angle C, could have been obtuse. Unfortunately, the sine inverse will never tell us that. And so, that being said, I can go back up to the top here and just say, if, the highlighted part here, if the angle is unknown, you must check for the ambiguous case by doing the following. You find the acute angle, that's C hat, by using the law of sines, and then determine if the original triangle with the original given quantities can support the supplement of the acute angle that we just found. That is, if we do this C hat here, and we find that it's roughly 23.7 degrees, which it actually is, then what we're going to do is we're going to say, okay, well, C is 23.7 degrees. Then we need to ask, wait, hold on, will 180 minus that C hat also fit? Would that, will that have fit? That's actually improper English. So let me trade out will for would. So would 180 degrees, the supplement basically, would the supplement of our reference angle have fit? And so the supplement of that 180 minus that answer would be 100 and, let me do this, would be 156 point, roughly 4, we'll say. Actually, it's 0.3 degrees, 156.3 degrees. With the original information. Well, the original information included a 37 degree angle. If you add 156 to that, that's greater than 180. So the answer to that is no. 37 degrees plus 156.3 degrees is greater than 180 degrees, implies no. We do not have a second possible triangle. But if it was a small enough angle, then let's see, determine, I'm just reading this right here, determine if the original angle with the original given quantities can support a supplement. If so, then there's a second triangle and you must create a second table for that second triangle. There we go. Now, again, I'm not teaching this, I'm just reminding you of it. And also because I was not your teacher for trigonometry likely, then it's probably a good idea to understand my thought process. All right, so let's take a look at an applet that somebody created on GeoGebra so that we can really see what the law of sines truthfully means. Usually when you're dealing with the law of sines, there's several different cases you can deal with. I don't like to have students memorize side angle side or side angle or anything like that. Instead, we just built a table. If you can use the law of sines, you have a complete row that's been filled out. Actually, I should say that the other way. If you have a complete row filled out, you can use the law of sines. Otherwise, you have to use the law of cosines, which we have not reviewed yet. But here's a case where you can use the law of sines. Somebody will hand you an angle. It's this angle right here that I'm just fiddling with. Let's just put it back at 52 degrees. And they give you a couple sides. Now, that's not actually always true. They could give you a couple angles on a side too. That's not the ambiguous case though. The ambiguous case is when you're given two sides and an angle not between them. So you can see I can adjust that side as well. Now, let's suppose that I keep this, or I reduce this side length here. Let's just say that this was the information you were given. Can you even make a triangle? And the answer here is no. That side just swings back and forth. It'll never touch the horizontal side. So there's no triangle there. If you start to increase this angle though, at some point it'll be just long enough. In fact, let me go ahead and just increase it a little bit more. Just be long enough. And maybe I should decrease this to where I know I have a, so here we go. Any length below that, and it's just going to swing. It's going to swing forever. Never going to get a triangle. But then if you just increase this just enough, it's supposed to be at 8, but for some reason it's only going to accept 10. All of a sudden you get a triangle. And in fact, let me decrease that a little bit. See if I can get this going just at the right angle. So boom, boom, boom. 7.8 seems to be, they must have some, anyhow, excuse me. At some point, it'll strike the horizontal axis and create a right triangle. And then you have this one triangle. So there's a triangle solution. However, if you make this slightly longer, it strikes the x-axis earlier and you get a wonderful triangle there. But then you'll get a second triangle as it swings around to here. So the first triangle is created by using that inverse sign. When we solve using law of sines, we get that acute angle. Notice this angle here between the green line and the horizontal axis is an acute angle. And then when we check to see if the obtuse angle, the supplement of that acute, is also a triangle, we find out in this case that it can create a second triangle. So this is a visual of why you can possibly get two triangles when using the law of sines in the ambiguous case. And then if this side length is just too long, you'll get a triangle here, but then it'll never come back to create a second triangle. It's just too long of a side. It'll never hit that horizontal axis to create a second triangle. So you only get the one. So again, there are those three cases, really. You have, four. You have first case here where the side length is just way too short. You're never going to create an angle. The second case where the side length is just long enough to barely touch into the horizontal axis and it creates a right triangle. The third case where the length is long enough to where it hits and creates a triangle, but then the supplement of that angle is such that it will create a second triangle for us. And finally, the last case where the side length is long enough to where it creates a triangle, but not a second one. Now, despite not being a review, I have actually reviewed quite a bit, right? You could probably tell that I've spent quite a bit of time trying to build out the ideas, because law of sines, the ambiguous case specifically, is usually a tough thing for students. However, once you see how I do the problems, you'll find out that, oh, it's not too bad. So let's start into real examples here. Sketch the triangle and solve. So in this case, we have a triangle where an angle's been given. Angle C is 68 degrees. Well, here's the deal. I normally don't sketch it first. I normally draw down the table first. So maybe I should do that first. I'll just go ahead and list out the table. So the table, I have angle A, Let me zoom in so that I don't make any mistakes. Angle A, angle B. Normally I don't even use the angle symbol. And then angle C. Of those three, I was given angle C as 68 degrees. And then side A, side B, and side C. And of those, I was given side B, 12, and side C, 12. Notice that I have a full row. This tells me law of sines is usable. Now I'm going to go ahead and draw this just very quickly. I always have a horizontal side for my triangle. So here's the horizontal side. And we were told that angle C, the angle they give me, I just park right here. So this is my angle C. I don't always write angle A right there. They told me that angle is 68 degrees. Luckily, I have a ruler that allows me to do that. So I'll just do that. And we'll just say this is of whatever length it is. So that's our angle C, 68 degrees. And they tell me the side opposite of that is length 12. Now, that being said, let's actually just pretend as though, or maybe I should say, when I'm given something like this, obviously side length C is opposite this angle C. So that's like side length C. But I always give the other known side right here. So this other known side, I'm going to call side B. That's the other known side. So if that's of length 12, then side C is of the same length. And so it's probably like this, honestly. So I'm just going to draw this out here. Something like that. I'm not too super concerned about that. So this is side C. And let me turn off my ruler. I don't really need it. This is side C, and this is of length 12. That's a visual of what's going on. There's no real reason. And notice my horizontal side is too long. That doesn't actually matter. This is angle B. This is angle A. I totally get that you know what angle B is because side C is the same as side B, but let's just pretend as though you didn't. Okay. How would you solve this? Well, you have a full, complete row. So you know that the sine of angle B, let me write that in here, sine of angle B, is to side B as the sine of angle C, angle C was 68 degrees, is to side C. Multiply both sides by 12, right? You get sine of B. I'm just showing you the mechanics of how it would have worked if this wasn't such a nice example. And then take the sine inverse of both sides. And you would get that the reference angle, which is sine inverse of the sine of 68 degrees, which will actually be 68 degrees. The reference angle is 68 degrees. And then you would ask, so let me fill this in, 68 degrees. We know that's 68 degrees. We would have known that's 68 degrees just because the side lengths are the same, but don't worry about that. Then we ask, is 180 degrees minus 68 going to fit? So would that have fit in the original triangle? Well, I'll tell you right now it won't, but let's go ahead and just do the mathematics here. This 180 minus 68, that's 112 degrees. And if you had tried to fit a 112 degree angle right there, let's just pretend we did, then what would we have left over for our last angle? Well, basically what I wrote in there, a big fat 0 degrees, because we would have 180 degrees taken from the angle B and angle C added up. So the answer to that is no, there's just not enough room for us to create a second triangle. So I'll put a big fat no, and then we can solve the rest of this triangle very easily, because once we've used the law of sines to find that angle, then we can go ahead and fill out this angle by taking 180 minus two sets of 68s. That's 120, 136, which is 44 degrees. Let me just double check. 120, 120, 160, 172, 180. Yes. And then to find that missing side A, we'll just do one last law of sines. Side A is to the sine of its opposite angle 44 degrees. As side, I generally just choose the side they've given me. Side C is to sine of its angle 68. There will be no ambiguity here because we're not using an inverse sine. So side A is therefore equal to 12 over sine of 68 degrees times the sine of 44 degrees. And that's approximately, grabbing a calculator here, I'm just going to type it in, 12 times sine of 44. Sorry, you don't need to actually hear me typing, do you? Sine divided by sine of 68. And I get roughly, I'm going to round to a single decimal place, so that's 9.0. It's not actually 9.0, it's 8.99 and change, but I rounded to a single decimal place, so 9.0, approximately, by the way. There we go. All right, so we've actually sketched and solved the triangle. And the big key here is just that we started with a full complete row. That was it. Once you start with a full complete row, you're using the law of sines. So let's try this again. Sketch a triangle and solve. And again, I'm going to just build a table off to the side here. Angle A was not given, but angle B was. That's 29 degrees. Angle C was also given. That's 100 degrees. That's a very large angle. And then our known side information is only the lowly little 115 for side C. I could draw this out, I suppose. It might be a little bit artistically incorrect, but we could try it. And I did my best there. Let's see. This is angle A, this is side A, this is side B. All right. But really, when I do this, a triangle, at least a drawing like this, doesn't super help out unless I have the ambiguous case. Now let's take a look at what we have here. We see that we were given a full row, which tells us law of sines, free to use. So let's go ahead and use. So I'm just going to say this implies use law of sines. That's what I use for law of sines. So imply that we're going to use the law of sines. So doing the mathematics for the law of sines, I can go ahead and take side B, the ratio of side B to the sine of the angle B, and say that's the same as the ratio of side C to the sine of the angle C. Multiply both sides by sine of 29 degrees, and you'll get what side B is. Side B is equal to 115 sine of 29 degrees divided by sine of 100 degrees. Now, I did not, actually I could have very easily just written down what angle A is. I just forgot to. Generally, I just dive right into the problem. But let's go ahead right now. I'm just going to pause and then figure out what this number is. And I get it's approximately 56.6. So that's what side B is. Approximately 56.6, whatever units they're using in this problem. And by the way, like I said just a moment ago, we could totally figure out what this missing angle A is. I should be using a different color for the stuff that I'm filling in. So 56.6, just because I want you to know the black ink was what I was handed. The blue ink is what I'm filling in just from logic. So let's see, 180 degrees is what a triangle will have. 100 of it is taken there, so we only have 80 degrees left. And then here's another 29 stolen away right there. So that gets us to 51 degrees left over for this angle right here. No arguing that. And then we can go ahead and use law of sines to find out what that missing side A is. Now, when you find that side A, so let's go ahead and do that. Side A, let me use black ink just for my work. Side A is to the sine of the angle A, as when you find that, do not use your approximated side here for the law of sines. Just continue using this highlighted piece. So we're going to go ahead and say A is to the sine of A as C, which is 115, is to the sine of its opposite angle 100 degrees. Thus, we get A equals 115 sine of 51 degrees divided by the sine of 100 degrees, which is approximately 90.8. So I'll just say this is approximately 90.8. So we have solved that right triangle. We solved that triangle. And so we have all the information we need. Again, when you are doing your computations, do it with the given information if you can. Otherwise, you risk rounding errors. So that's a piece of advice. For this one, I'm not going to bother sketching unless I really feel the need to. But let's go ahead and just write down the information. Angle A, so we use black ink here. Angle A is given as 125 degrees. Angle B, we do not know. Angle C, we do not know. I can say this, though. There's not going to be an ambiguous case here because of the fact that we already have an obtuse angle. So you're not going to have two obtuse angles in a triangle. That's just not going to happen. So I know that there's not going to be two triangles. However, this is, by all rights, an ambiguous case still. You won't be able to see it until we start doing the problem, but it is an ambiguous case because we're missing an angle. And when you're missing an angle, that tends to be an ambiguous case, or that not just tends to, that is. So let's see. We have a full row. So a full row implies use law of sines. And now we'll go ahead and use that full row to help us find angle C. But when you're finding an angle using law of sines, again, that implies you possibly have the it is the ambiguous case. You don't know. Do you have no triangles, one triangle, or two triangles? So let's go ahead and do the computation. Let's see, the sine of that angle C, and by the way, I didn't put the brackets on that angle. Sorry about that. The sine of that angle C is to its side as the sine of angle A is to its side. Multiply both sides by 45. So you get that sine of angle C is 45 times the sine of 125 degrees. All this stuff I should really have just paused so that you guys don't have to watch me do all this. And then we'll take the sine inverse of both sides. Now, this is such a special case that I want to showcase my computations here. Notice I'm in Desmos and notice I'm in degree mode. I'm just going to do the arc sine of, let's see, we had 45 times the sine of 125 degrees, and that was divided by 20. Just double checking. Let's see, sine inverse 45 sine of 125 degrees all over 20. But if you look at this answer on the right hand side, it says undefined. And that is because if you take a look at this fraction that we have here, 45 sine of 125 over 20, that's greater than 1. You would not know that until you grabbed a calculator, by the way. So this is kind of the punchline. If you grab a calculator and it returns undefined, then you know there's no triangle. This is that weird case where you have a horizontal side, they've given you an angle, 125 degrees here, and that angle again is angle A, and they've given you a very short side length A, and there's no way for that side length when it swings to ever connect into the horizontal axis there. And so this is that odd case where you're just not going to get a triangle. You won't know, generally speaking, until you grab a calculator. And so your calculator is going to tell you if you have the undefined case. That's kind of nice. So anyhow, that's one of the ambiguous cases where you're given a full row, so you can use law of sines, and the row with the missing piece has the missing piece being the angle. That's the ambiguous case, and it could lead to no solutions or no triangles, which we get here, or it can lead to one solution, which happens quite often, or it can lead to two triangles. In this final example, I'm going to show a true workflow, like how I would do everything from beginning to end. And this is actually an ambiguous case where we're going to end up with two triangles. But it's very important to follow kind of my advice here, because you'll end up suffering round off errors if you don't. So let's go ahead and at least build the table. We have angle A, which we were not given. We have an angle B, which we were given, and that was 25 degrees. We have angle C, which we were not given. And then we have side A, which we were not given, side B, which we were given as 25, and side C, which we were given as 30. Now, I'm not going to bother sketching. And usually something like this, it'd be kind of unnecessary to sketch something like this. It's kind of a terrible problem to sketch, honestly. So let's see. I see that I have a full row. So I know I'm going to use Law of Sines. So let's go ahead and find angle C. Angle C, I'll do all my handiwork in green here. Sine of angle C is to side C as sine of angle B is to side B. Multiplying both sides by 30 and taking the sine inverse, we get the following. C is equal to sine inverse of 30 sine of 25 degrees over 25. Now I'm going to go ahead and head to a calculator, and I'm going to save these values in as I work, because it's critically important that I do that so that I don't suffer from round off errors at any point. So let's go ahead and go over to Desmos. In Desmos here, I'm going to say C is equal to, and then we have the sine inverse, which is the arc sine, of 30 times, let's see, we had the sine of 25 degrees, and we're going to go ahead and divide that sine of 25 degrees by 25. And you get this approximation for the angle C. So I'll go ahead and write that in. C is approximately 30.5 degrees, and I'll even write that up here. Now remember, this, we might have an ambiguous case, so I'm going to come back to this in a moment. But while I have that near exact value in Desmos, I'll continue this computation. Again, this is to avoid round off errors. So angle A, I'm going to use Desmos to help me compute angle A. I totally get that you're going to say, well, wait, angle A is just 180 minus angle B minus angle C. And it totally is. But I just want to avoid round off errors, so I'm going to save angle A in Desmos. So hopping over to Desmos, I'll just take 180. Let me go ahead and do this. Angle A is just 180 minus angle C. Notice that I can use that minus 25, which is the angle B. And I get 124.5. And I write that in there. And it would have been the same, by the way, had you just typed in 100, have you just done 180 minus 25 minus 30.5. But the critical part here is the fact that I saved that value of A in my calculator, because I need to find side A, and I don't want to use 124.5 for that. Instead, I'm going to say side A is to the sine of its angle A. And notice there, I didn't write sine of 124.5. The reason why is because that's just an approximation. I'm going to use Desmos' version of A, angle A in this instance. And that's the same as the ratio of side B to sine of angle B. And in fact, those are solid 25s. So 25 over sine of 25 degrees. And therefore, I can just quickly write side A is equal to 25 sine of angle A over sine of 25 degrees. And now I'll go over to Desmos and compute that. So here, I'm just going to go side A is equal to 25 times the sine of angle A, which we have saved in there, divided by the sine of 25 degrees. And we get 48.7 is the length of A. That's rounded to the nearest decimal place. So I've written that in there, and I'm going to go ahead and go up here and just say this is roughly equal to 48.7. Now, I just want to draw your attention to the fact that had I not used A, and instead I used this approximate 124.5, I want to show you how that would change the value. It won't change it too much, but enough to where you'll be off by a decimal place. So let's just take a look. So instead of angle A, had I done sine of 124.5, I would have gotten 48.75, which rounds to 48.8. And that is not the same as 48.7. And you may say, but that's only a decimal place off. And I would say, yep, but still that's a decimal place off that if you're using an online homework system, it might just mark you off. And that's a super huge frustration. So just use as exact as a value you can get, which is basically saving your values in your calculator as you go forward. Now we're not quite done with this. In fact, we're only halfway done with this because there might be another triangle. So we should ask that right now. And I'm going to zoom in just to ask that question. How do you know? I mean, how do you know if there's another triangle? Well, this was the ambiguous case. So really, when you do this, you should just say, check for second triangle. The moment that you have to use the law of sines to find an angle, you should always check for a second triangle. You should state that you need to check for a second triangle. That will remind you to go back and say, okay, well, will 180 minus that number fit within this triangle? Remember, the law of sines only returns an acute angle. It will not return an obtuse angle, so you don't know if that angle could have been obtuse. And it turns out 180 minus 30.5 is 149.5, and the given information was the black ink there. So the only other given angle was the 25-degree angle. Well, 149.5 plus 25 is still less than 180 degrees. So yes, the answer is it can totally lead to a second triangle. And in fact, 180 minus, like I said, 30.5 gives us 149.5 degrees. But remember, we still had a 25-degree angle given to us initially. That was angle B. And so this is equal to what? 174.5, I think? 174.5, which implies we still have 5.5 degrees to give. So for angle A. So that means that we do have a second triangle. The way that I draw out a table for a second triangle is I write down all those letters, but with bars over them. Just like that. And then I fill in the given information, still using that black ink. So C bar doesn't, side C bar doesn't change. It's still 30. Side B bar doesn't change. That's still 25. And angle B bar does not change. That's still 25 degrees. So that stuff is concrete. But angle C bar, that is no longer 30.5. It's 180 minus how we got 30.5. We got 30.5 using this computation. So I'm going to redo that computation in Desmos, and I'm going to take 180 minus that. That'll be my new value for C. So here was my original computation in Desmos. C is equal to that 30.5. But I actually want the supplement of that, so I'll take 180 minus that. That will be my new value for C. So I'll just hit enter. And back on my paper here, I just write in that approximated value, but that's not what I'm going to use for my computations, but that's my approximated value. Now I need to approximate the value for angle A by taking 180 minus that value of C minus 25. And so I go to Desmos for that. And I just say angle A is 180 minus the 25 degree angle for B minus the angle C we just computed. And that gives me rounded 5.5 degrees. But again, that is totally rounded. So I do not want to just type in 5.5 degrees for any other computations. I'm going to use that saved value of A. So again, I'm just showing you a streamlined workflow. Now, to find that missing side A, I will just do all my computations off to the right here. Missing side A bar is to its sine of its opposite angle, A bar, and again, you often with a law of sines, you'll want to use the given information to compare with. So side B is to sine of angle B. There we go. And that implies that A bar is 25 sine of A bar, the angle, over sine of 25. So let's go ahead and go into Desmos and compute that. So we have 25 sine of that angle A divided by sine of 25. And we get 5.6, rounded to a single decimal place, 5.6. And there you have it. You have both of your triangles completely solved. That was a law of sines ambiguous case problem where it leads to two triangles. And I paid close attention to not using rounded values in my computations. Had I used rounded values in my computations, everything gets a little screwy as time goes on. That last computation might not have been too bad, because we, instead of using A here, we would have used 5.5. And we would have gotten to 5.7 as our rounded value. So it would still be off by a decimal place. So this is just to show you a little bit of care when doing these problems goes a long, long way. All right, that's it for this video. I hope that you I hope this review was good for you. And that it kind of stoked your memory on how things work. I do want to, again, drive home the point that you want to make sure that you save your values in your calculator rather than using approximated values throughout. That's critically important because as we move forward, you might do maybe 10 computations in a row, and if you keep using rounded values each time, the error just grows and grows and grows.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.